Screen is visible? Hello? Uh,
Yes, sir. Yes, sir.
okay, the slide is visible, right?
Yes.
So, yeah. So, this is basically the fourth lecture. So, we will be continuing with the MOS characteristics. So, today we'll see about the body effect and also some of the parasitic capacitance, that exist in a MOSFET. So, what are the different types of capacitance that you will see that we will be seeing and discussing today? How do we calculate the parasitic capacitance, and how do we estimate that? So, let's start with the body effect. So, what is body effect? So, what happens is we know that this is a PMOS device, and you know, and this is the connection to the substrate. So, in this case, it's P-type material, P-type substrate, and we have this connection to the body, and we have this, we have this source and drain, right? So this is basically the body connection. So whenever this body connection it has a potential which is even lower than zero, right? Which is lower than zero. Suppose this is source is connected to the ground. So whenever this body terminal has a potential, whether uh, less than zero or more than zero, this will affect the threshold voltage of the MOSFET. So there can be a situation where these two nodes are at different potential. So whenever the source and the body are at different potential, then the threshold voltage will be modified. It will not be the normal threshold. The threshold will be modified. So we can see here, this is the symbol of the NMOS. The VG is connected here, the source is connected to ground, and you know the this bulb terminal is connected to a potential less than zero, and of course drain is connected to a potential VD. Now we may say, look, why, like, when this case is possible, like that. Generally this will be connected to the ground, and it cannot go below zero. But this situation can arise. I'll show you the cases when this arises. In fact, it arises multiple times, many times, most of the times, like that. And so this situation will definitely arise like that. So now whenever this potential, the bulk potential, goes to a value less than zero, uh, this phenomenon happens like that. So whenever these both are grounded, whenever the bulk and the source are grounded, so normal operation happens. So in this situation, this both are sorted. So it's a normal situation. There is no change in the threshold. But whenever this VV, the bulk, is at a potential lower than zero compared to the source, so what happens when this bulk is at negative potential, right? This will be repelling the electrons, and because of which, as we have discussed last time, right? The depletion charges will increase. Suppose this is the situation when the channel has not been formed, right? So in normal situation, what happens? This first depletion layer happens, right? Layer happens, and then if you increase the potential, then there will be free electrons where the inversion happens, and then current starts flowing. But whenever there is a potential, when the bulk is connected to a potential lower than zero, right? Compared to the normal situation, more number of depletion charges will be there beneath the channel, because this negative voltage will repel more electrons, and more number of these charges will form like that. So now what happens? So the amount of VG required to create the channel will be higher, because I don't know, like, if you remember, the threshold voltage is a function of the depletion charge, right? This is if we see in the equation, right? If we see in the previous lecture, if you see in the equation, so this is the this is the this is the basically the definition, or this is how the threshold voltage comes. Like, threshold voltage is a function of the Q depletion, which is the depletion charge beneath the channel, right? Let me copy this. So if we go back here, I think I cannot copy that one. Anyways, so from there we can see that the threshold voltage is a function of the whatever the charge that is formed here, and because of the negative voltage, because more number of these depletion charges are formed, that's why the threshold voltage increases. So it can be shown that the threshold voltage can be written like this. So VTH equal to VT0 plus this gamma, and we have this this value. Again, this phi f comes from the definition of whatever we have discussed, like whatever the formula derives on lastly. So it is basically depending on the Fermi level, kind of it's like the potential, like that. So again, this comes from the device physics, like that. So, and this VSB is the source bulk potential. So in this case, because this VV is negative, source bulk potential happens to be positive. So because the bulk is at a lower potential and source is at higher potential, so the VSB happens to be negative. So in this case, if positive, VSB is positive, then you see that and the whole the threshold voltage increases, because this whole terms becomes positive, so multiplied by this gamma, so you can see that VTH is positive. So VTH0 is the threshold voltage when the bulk terminal is connected to 0. Clear? Hello?
Yes, sir. Yes, sir.
Okay. Any questions?
Yes, sir. Yes, sir.
Any questions?
Sir.
Yes.
Sir.
Yes, I can hear.
Sir, about VB, body voltage.
Yes.
It is external or internal?
This is inside you see, this is internal, because this is internal in the sense that you are telling in terms of IC, integrated circuit, or what do you mean by internal and external?
I mean that it is externally applied or internally developed in this inside
no,
the
no,
circuit.
this is externally applied, like that. This is externally applied.
Then, sir, I have a question. It is increased. It is advantage to increase the VTH threshold value for us.
If you want to decrease that threshold, so if we increase it, the threshold voltage will decrease. Yeah.
Sir, why we are manipulating this threshold voltage?
Okay, so what happens, even if we don't want to manipulate also, situation arises where we have to where this situation arises. So I'll show you the situation. Now suppose I have two MOSFETs, this NMOS, right? They are connected something like this, right? So now, as we know that all the bulk has to be connected together, because they are all sorted, right, from our previous discussion, right? And this will be generally connected to the ground. This is generally connected, and suppose this is connected to the ground, right? Situation is clear, right? So I have two MOS. Let's name them M1 and M2, and both the bulk potential are connected to the ground, right? bulk potential is connected to the ground, and this is also connected to the ground. Now for this transistor, right, for this transistor, the source of M1, which is basically the drain of M2, will have a potential more than 0, right? Hello, I think there is some noise. So there can be a situation when this source potential will be higher than 0. Definitely, right? Because this is a drain. Some situation may arises when this source of M1 is higher than 0. So this potential is basically higher than 0. So the potential at this point V is, or Vs maybe, is greater than 0, right? So then what is happening? The bulk is at 0 and this node is at a potential higher than 0, right? So then the threshold voltage of M1 will be modified, and it will be you will get the threshold voltage of this M1 based on this equation. Like, it will not be a normal threshold voltage. So this kind of situation where we are like when we are staking number of this kind of transistor, so this situation arises like that. It's not that we are purposefully trying to manipulate the threshold voltage. We may not do it, but this situation will arise whenever we are staking multiple transistors like this. So what happens for this case? The source voltage will be higher than 0, and this is at 0 potential, right? So that's why we have this VSV, source to bulk potential becoming positive. Clear? Is it clear?
Yes, yes, sir.
Yeah. So
Excuse me, sir.
yes, yes.
Sir, I wanted to ask that, is it advantageous that V threshold is increasing, or it's a demerit? I mean, is it good or is it bad?
It depends upon the situation, right? Because what happens is if the threshold voltage is increasing, then the amount of VGS that required becomes higher like that. So we cannot directly tell it's good or bad. It depends upon the situation like that. So
And sir, one more thing, that in VGS, like in here,
yes.
threshold voltage is basically the voltage at which the number of the negative charge and the positive charge becomes equal, right?
No, threshold voltage is the voltage at which the inversion layer is formed here.
Inversion layer is formed.
Yeah, so that the channel is formed, right? Yeah, so basically it is sufficient enough to flow the current. Right?
Yeah. So, sir, in this case, if we just see, if we don't see the equation right here, if we just see that in figure 1 that you told, when V bulk is 0, then there was just one layer of electrons, one layer of negative charge, without increasing the VGS, without changing anything in the VGS. Now, in the second figure that you showed, V bulk is less than 0. So, I mean, the number of electrons, the number of negative charge is increasing. So, basically, less voltage is applied from VGS so as to create the inversion layer, right? So, how is the V threshold increasing in that case? It should decrease, right?
No, yeah, your question is correct. You see, this is the this is the depletion charges. This is not the inverted charges, right? So what happens is, whenever there, as you have rightly pointed out, whenever there is less negative, the depletion charges increases, right? So then what happens? You need more voltages to create the inversion layer, right? Because this is depletion. This is not responsible for the for the conduction of the current. So we need to invert the channel, right? We need to invert it like that. Are you getting my point? And if you see here, if you go to the previous this one, so if we go to the previous discussion, so we need to create this channel, right? So we need to create this. These are depletion. These are not responsible for the carrying of the current. So we need to invert the channel so that we have free electrons from the movement of the current, and that's why we have this equation, like where it comes that this depletion region, like that, these charges is responsible for this, threshold voltage, like that. It comes into the picture.
Okay.
I hope it's clear now.
Yes, sir. Yes, sir.
Okay.
Thank you.
So yeah, so
Sir,
yes, yes.
sir, I have the same question as she asked, but sir,
Yeah.
hello.
Yeah. What is the but? Yes.
Sir, when VB is less than 0, you said it will repel the electrons.
Yes. Yes.
Sir, in the depletion, the ions are formed there, right? Near that channel.
Yes. Yes.
So the VG we are providing, it should be less because the free electrons can be formed easily, right? Because they are already, the ions are formed, because there are no more like the positive charges like to be made to ions, so it should be less, right?
So it's not like that. It's basically what happens is the the VG required becomes higher actually to make the channel, like that, to get the amount of electrons, like that.
Sir, it's not about the ions, free ions, right? As you said, it's about the electrons that we are.
Yeah. That it's about the
that
electrons, that free
right?
electrons that we need to form. Yeah, that's true. Yeah.
It's not about the free ions, the negative ions that are there.
Yeah. It's not about the negative ions. It's the free electrons that we need to form beyond that, like that.
Okay.
Okay. Yeah. Because this ions is not responsible for the charge, current conduction. The free electrons is responsible for the current conduction. Okay. So now we'll move next. So what happens is because of this, the bulb terminal is also because it's modifying the threshold voltage. So sometimes this is also called a back gate. Back gate, because we already have a gate, so this is also influencing the channel property. So this also acts like a gate, so that's why, if you see here, if you see here, suppose I have like created this situation where this VGS is sufficiently higher than the threshold voltage, right? This is drain, this is source, and suppose we are varying the bulk potential. So what happens whenever the bulk is very, it's the bulk potential is very low. Basically, this VSV is very high, right? Then overall the threshold voltage is very high. So then the current flowing through the through this transistor can be, we can even make it zero, like, so it acts like a gate. We have this, of course this thing is not used much. It is just to theoretically show that how the threshold voltage can even manipulate the current profile. So you can see there here that whenever the threshold, this VSV is very high, VSV is very high, this is very low, very negative compared to zero, then the current IT flowing through this transistor is almost zero. Then as we make it less negative, then at this point when this will get the this is the situation where we have only this point, this is zero. So we can see like how the threshold voltage threshold voltage is manipulated by the this bulk potential, and that's why it's sometimes termed as a back gate, because it's like a gate. We are able to manipulate the channel current, manipulating this one. In fact, in some of the process, even this threshold voltage is manipulated just to get some functionality. Of course, it's not done; it's rarely done. But some people may have try doing this kind of experimentation, like in some circuits. Okay, so I hope it's clear. This is a simple one. Next is we'll little bit discuss about the MOSFET layout, and finally then we'll directly come to the parasitic capacitance part. like that. So we as we have seen like multiple times, we know this is the source drain region, this is the gate, and this is the oxide, and these are the place where these are the contact windows, or these are the metal contacts where the source and drain will be connected to the metal layers. So generally first it's connected to M1, right, from here, and then it can be connected to higher region. So this is how this layout looks generally in Cadence. Whenever you are doing the layout, you will see this kind of, and this is the L drawn. So whatever you have drawn, the length of the channel, of course, as we have seen before, the effective channel length may be little smaller than L drawn, but yeah, and that's fine like that. So this is the L effective because of this source and drain getting beneath the because they have moved little bit inside the this gate region, so it can be little smaller, the effective one. Okay, so these are some of the layout examples. So I have this transistor, like this is transistor M1, this is transistor M2, and this is transistor M3. So the gate of M1 is this A, and gate of M2 is B, and this gate of M3 is connected to this point C, and this C point is connected to the source of M1 and to the drain of M2. So we can lay out the MOSFET something like this, right? So this is my M1, this is M2, and this is M3. So basically in this diagram, the this source and drain contact is not shown, but it is something like this. So here what we are doing is we are trying to share, for this M1 and M2, we are trying to share the contacts between the source of M1 and the drain of M2, something like that. We are staking like that. We are staking all the transistors. So M3. So then again M3, the source of M2 will be connected to the source of M3. So this is the point N node, where this is the source of M2 and source of M3 are connected together, right? So now of course we need to connect the gate of M3 to the this point C point. So this gate will definitely be connected here, right? This need to be connected, and the gate of M1 is this point A, signal A, and gate of M2 is the signal B, right? And of course the E is the E point and F is the F point. These are two open nodes, right? So this is how it is shown like in actual connection. So I'll have a context here, which will be connected to, this is basically this line is M1, so it will be connected to M1, and this is the point where there is this contact, and it will be connected to the point B, so like that, point B, and this is the point this point N. Of course we have this terminal here, so it can be directly connected to the M1 here, and this this is poly of M3, as I have shown this connection, something like this. So what it will do is this poly will be connected through this contact to M1, and then again it will go, and then through this contact it will be connected to this point C point, right? This is the C point again, and this is the N point. So of course we can connect this E point from to the metal wires, so it can use for routing, and then again this F point again it can be connected to metal one, and it can be used for routing. So this is how if we have this kind of structure, we can share the drain and source of two transistor, and we can have a very compact layout. So what happens is because of this, we'll see later on that the junction capacitance reduces because we are clubbing the source and drain. That we'll see later on, right? Because we are off this clubbing, there is an advantage of decreasing the junction capacitance. I hope this is clear. If it is not clear, let me know. This layout.
Sir,
Yeah. Yes.
Can you please explain that third diagram once again?
Third diagram. Okay.
Yeah.
So did you understand the second diagram?
Yes, sir.
Okay. So if you understood the second diagram, you see the M2 is this has to be connected to gate of M2 will be connected to B, right? B point, right? So currently this is a polysilicon and we have to go to metal one, right? So through a via, so this black dot is called a context or sometimes it's called via, right? All these black points. There's context or even it's sometimes it's called via basically. Via means the connection from poly to metal one, right? In the upper layer, metal one will be there, right? This B point is connected to again to metal one. Again here also you can see that through this contact this A point will be this point will be connected to A. Now we need to connect this M3 with the point C. So this gate of M3 will be connected to the point C, right? So the point C is here, right? Point C is here. So this polysilicon will be again connected to the metal M1 through this contact, and then it will be connected here, right? So it's layer by layer, right? So in the first we have this active layer, then we have this polysilicon layer, and then above that we have is metal layers, right? And through this context only or through this via only we are doing the connections, right? We are doing the connections between the polysilicon and metal layer. Is it clear?
Sir, yeah, the point N, we have this thing, right?
N, yes.
What is contact? Yeah. The left to this black contact.
Okay, this one. What is the use of that one? You're asking me what is the use of this one? Hello?
Yeah, that one, yes.
Yes.
Sir.
You see, like in this situation, according to the circuit, this point is a terminal of this whole circuit, right? So I need to have connection between this from this point to a metal one here, right?
Yes, sir.
So that I can do the connection with some other circuits, right? That's why I am doing this connection. Yeah.
Yes, sir.
So because we need all this A, B, N, E, F, right? All these are terminal, like for this cell, right? That's why we need to make the connection with M1 so that we can then again connect with some other circuits like that.
Yes, sir.
Clear? Okay. So again, this was little not complicated. This is simple only. Now, if we come back to the simple inverter also, this is a layout of a simple inverter. Of course, again, because I am taking images from the different books. That's why this diagram will seem little different here. So, and actually, when although this is now shaded, it's only black and white. Actually, when you'll be doing a layout in Cadence, all these layers will be of different colors. So you'll see very colorful, the layout, because then we need to identify, right? Here we are not able to identify this is what layer, whether this is metal one or whether this is, of course, in this case the poly is dotted here. So, but in actual when we are doing the layout in Cadence or like in Cadence basically, we'll see that all these layers are colored differently so that we can identify easily. Like that. So in this is a case of this is an example of inverter layout. So I have this inverter. Ground. This is my input, right? It's output. So we can see here. I think. How many have you done? How many have you are familiar with Cadence or done layout in your undergrad? I know it's difficult to, but anyone who has not yet done layout or who has not used Cadence, just curious.
Sir, I haven't.
Okay. So there are a few people, right, who have not done layout, or who are new to all this, like that. Hello.
Yes, sir.
Yes, sir.
Okay. So basically, this is this is the N well, right? You can see here this is N well, where uh, this is how the N well is drawn. So in cadence, what it will be there is there will be a symbol where it will say then this is N well. Some red color, and then there may be some different color, different color codes. That's pink, like that. So this pink may represent maybe this p plus region, right? There is this p plus region, and there is n plus, or of course the the substrate connection is not shown here, but there will be a body or bulk connection, right? So there will be something like say p plus region, and then suppose some green color. I'm just using some random color, but this is the n plus region. N plus region, and then let's take some. So this is the metal one, which is connecting basically the drain of this drain and drain of this PMOS and drain of this NMOS. So something like M1. So through this contact, it will be doing the connection, and of course this is also M1. This also is M1. I think these two colors are quite similar, difficult to distinguish. So some other color, maybe blue for M1. And this is also M1, which is connecting to the P-tab. Okay, the substrate connection is here. Sorry, substrate connection is here. This is the drain. So this is connected to the VDD. This is not substrate. So this is connected to the N well. So we have this N well, then we have this P plus, so PMOS device. So this is connected to the drain source of this this one, source of this PMOS, and then the drain of this PMOS is connected to the drain of this NMOS, and we have this this dotted one is the black dotted is the polysilicon, like that. So different layers are different layers are denoted by different colors, and if you examine carefully, it's very easy to understand. So this in this N well, this PMOS device is drawn. So where I have this gate, so these two are connected using the polysilicon itself. Of course, we can go for you can go to metal one and also do the connection. It depends upon designer what way he wants to do it, and then the source of the PMOS is connected to the ground. It's little messy, but I think you can understand it like that. So is it clear or it's confusing? Hello? Hello?
Yes, sir, it is clear.
Okay. So there is another way by which we can do the inverter. So you can just maybe try to figure out yourself. It's not very difficult to understand. Just I should say just just sit yourself and try to analyze it. If you are not able to do it, let me know. So in this case, we have this bulb terminal is also there, like that. So this PMOS is there and this gate are connected. So again, this is the inverter, right? So Here we see the drain and drain of this this PMOS and this NMOS are connected through this metal layer, metal 1, and is connected to the output. And this is the gate. This gate is connected to this is a polysilicon, and this is connected, and this becomes the input terminal of the inverter. And this is the drain is connected to the VDD, and of course this bulb terminal is also there, which is basically the N plus. For PMOS device this is N plus, right? So because it's connecting to the N well, so then again it's also connected to VDD. So, and for the source the bulb is P plus, right? And this is again sorted together, because if you see here the bulb terminal will be here, they'll be sorted, right? Although it is not shown here, but in the later layout, example number 2, right? In the example number 2, even the bulb terminal is shown. Okay.
Excuse me, sir. Sir, will we have a practical on this so that we can get a better idea?
What I will do, currently our cadence is down, so towards the end of our course I will try to show some practical layout opening cadence, right? So we will not have any hands-on. If you are doing some kind of project or something like that in future, then it's possible. But what I will try to do is towards the end of this course, of course now we'll not go too much into the layout now. Later on we'll come back. This is just an introduction of the layout, so don't worry. So towards the end of this course I will try to show you the practical demonstration of all this stuff directly in cadence, like in the cadence environment. So then you'll get more, you'll understand more better, like more clearly. Okay. Yeah.
So thank you, sir.
Yeah. So I think I'll not go too much in depth now. We'll actually now we'll be just more focusing on the electrical characteristics of the inverters and different CMOS logic gates. So layout part will come back maybe towards the end, like that. So here I'm just trying to give some introduction like that, because we are discussing MOSFETs. So now there is this another concept of fingers, which is very important. So what happens? Suppose I am doing this. Layout of this MOSFET. So if this MOSFET is very big, although it's shown very small here, but there can be a situation where this W can be very high, right? This W can be maybe in the range of 100 micrometer or even higher than that, right? So then what happens is because this polysilicon, which is used to make the gate of the MOSFET, because this is not a very perfect conductor, although this is a good conductor, but it's not a very perfect. It has some resistivity, so because of which there will be a parasitic resistance along this gate, right? So especially it becomes very critical whenever you are designing very high speed digital circuits, and whenever the gate size or wherever the width of this width of this transistor is very large, then we have this kind of parasitic that is coming into picture. Even for analog design this is very critical, especially when we are going for very high kind of very big kind of transistors. So what happens is there will be a good amount of resistivity along this, like that. So not even 100 micrometer, I should say even lower will have even if it is around 20 micrometer or even 20 to 10 to 20 micrometer, and this kind of can be a problematic. And especially what happens is because of this R, of course there will also be a C, right, associated with this. Because of this RC kind of formation, it can affect even the speed of operation. And there are some other issues, even of course this is not valid for digital circuit, but for analog what happens is even these resistors will produce some noise and all like that in the circuit, like that, because resistor has its own it has its own noise associated with it. So all those issues will come up like that. So what happens is, to solve this issue, if I have to design a big transistor, this is split into something like this, right? So this is split into two parts, right? W is divided into 2. So basically, easy way to understand this is, if I have some kind of this transistor, I can definitely make 2 transistors, something like this, right? I can divide it into 2 half, right? So this width is W by 2, and this is also W by 2, right? So suppose, let me call this as, source and drain of this transistor, and let me call it, I can name it, I can make it as, drain and source, something like this. I'm putting this orientation, like. So what I have done is, I have divided this big transistor into 2 parts, like that, this one and this one, and now I can, I can connect this source of, I can connect this source and source together, and this drain and drain together, and get together. So in this process, what happens is, because I have divided this gate into 2 parallel parts, the resistivity basically reduces, right? The resistance here also it reduces, right? So this is a situation. What it is done is, this, because this is drain and drain are same, I can even club them together. So this is the situation. This is the same one. This is the same one here, where basically the drain of these 2 transistors are getting clubbed. So if I name it as differently, like this is source 1, drain 1, gate 1, drain 1, so drain 2, source 2, and gate 2. So then here it will be gate 1, gate 2, source 1, and this is combined drain 1 and drain 2, and this is, source 2. So basically, and this gate 1 and gate 2, because of, because of this kind of parallel splitting, making it parallel, the overall resistance reduces. So if this Rg was the resistance, like this is a symbolic representation of this one, right? So if Rg was the resistance of this gate, then if I go for this kind of structure or arrangement or layout, then my then my gate resistance reduces by Rg by 2, and here also it reduces Rg by 2, right? So that's the advantage of, or that's how this is called basically the fingers, right? So even in the layout, it will ask you, like, if you are drawing a transistor, how many fingers that you want to keep. So that this is called the fingers, right? So yeah, is it clear? Hello, is this clear?
Yes, sir.
Yes.
Yes, sir.
Okay, good. So if it is clear, it's good like that. So now if you see here also, if you see visually, if you see here, the overall area of the drain has reduced, right? Compared to, if this was the source and drain of the original transistor, the complete total area of the drain has reduced in this case. It is reduced in this case. So there is advantage in terms of speed going for this kind of this kind of fingering. This I will just come after just discussing the next slide. Why? Because what happens, because of this overall area reduction, the capacitance associated with the drain reduces, right? The capacitance associated with the drain reduces, and you know that the capacitance impact the speed, right? Speed of operation. So because of which this also influences the this also helps to increase the speed of the device. So suppose if I am now you may say, oh no, what's happening to the source? The area of the source is in fact little bit increasing, or the parameter is increasing, and because of which the parasitic capacitance may increase. But in some situation, the source generally will not carry a signal. So, suppose if I have an inverter here, this is my PMOS device. This is an NMOS device. This is VDD. This is input and this is output, right? So if you see here, the node that is carrying a signal, this is the drain of this PMOS and drain of the NMOS. The source are always connected to the ground, right? Source of the source of the PMOS is also always connected to the ground. So the node that is carrying the signal, basically the signal where the rise and fall times is an issue. So the capacitance at this node is more issue compared to the source. That's why when we go for this kind of fingers, because the drain is getting shared, so overall this area of the drain is reducing, because of which the parasitic capacitance associated with the drain reduces. Basically the drain to bulk capacitance, because of which the speed also becomes speed improves basically in this case. So when we'll discuss the parasitic capacitance again, I think I'll come back to this point, then things will be very clear. So MOS device capacitance. So there are different kinds of unwanted, like parasitic capacitance. Parasitic, the word parasitic means it's a parasite, right? Parasite means which we don't want basically. So these are the different kinds of parasitic capacitance that comes into that comes along with a MOSFET. So you see, people are going for higher technology node, right? 90 nanometer, 65 nanometer. We say that okay, 16 nanometer, 7 nanometer. Why we are going for very small device? The only reason is to reduce, right? Because these capacitance are associated with the geometry, right? We know that whenever the area is large, the capacitance is directly proportional to the area, right? The plate area, right? If I have two plates, right? If I have two plates, it is a capacitor C, right? So depending upon the area of this, the capacitance increases, right? Because it's directly proportional to the area. So if I reduce the size, of course it's also dependent on this distance. So if I reduces this size of the MOSFET as small as possible, then what happens? The parasitic associated with this transistor also reduces. That's why it is possible to go for very high speed operation. If I have to design a very high speed processor, all my individual MOSFETs should be of very high speed. Otherwise, all this capacitance, as you know, the capacitance it filters the high frequency component, right? So in that sense, it affects the speed of operation of the MOSFETs. So that's why what is targeted is to try to minimize this parasitic capacitance. So here we'll see what are these parasitics, where does it comes from, and how we can categorize it, and what are the different kinds of capacitance that exist in a CMOS device like that. So the first one is the C1, right? C1 is basically this. You see, whenever the MOSFET is carrying these charges, a channel is formed, right? So between this channel, it's like some kind of plate, right? With this channel, and we have this oxide, right? SiO2. SiO2 is there, and I have this gate, right? The gate is there, so which is basically a polysilicon. So beneath I have this channel. So between this now between this gate and the channel, there is this capacitance C1. So this C1 is formed between this gate and the channel, and I have this bulk terminal is there. So between this channel and the bulk is also one kind of capacitance C2 is formed. So this is also called depletion capacitance because of the depletion layer, like that. Now, as I have mentioned, because of the annealing process, the source and drain may go little bit inside, right? Inside the this gate, beneath the gate, right? So it may, because of which the we have come to the concept of L effective. So this drain and source will go little bit inside this gate region, and the drain also will go inside this, under this gate. So because of which there is an overlap here, overlap between this drain and the gate, and between the source and the gate. So this C3 and C4 are the overlap capacitance. So basically there is an overlapping and overlapping capacitance. Now this drain and source, this source and drain and the substrate, they are some kind of they are in a reverse bias condition, because there is this N and there is P. So this PN junction is a reverse bias condition, and as we know that whenever there is a PN junction, there will be associated junction capacitance, right? The PN junction, it can be sometimes used as a capacitor also, right? Variable capacitor. So this, depending upon the reverse bias voltage, right, there will be a capacitance of this PN junction. So this junction capacitance will contribute to the drain, and this also will contribute to the source. So if you see here, if you see this distribution, right, I have this gate and drain, right? So this the capacitance between the gate and the drain is termed as CZD. So you can see here, this one of the component is this C4, right? The C4 components comes here, and we have this CZS also. So again, one of the component is C3, and the other component comes even from the channel. That we'll see in the next slide how it comes. Then we have the capacitance from this drain to the bulk. So this is the bulk, right? This is the bulk, drain to the bulk. So because of this reverse bias, based on this C6 will come here, like that. Drain and bulk, this C6 will come here. C6 will come here, like that. And again, from this source and bulk also, this C3 will come here, basically. C3 will come here, this C3 overlap, sorry, C5. This depletion capacitance, because source and the bulk, there will be a capacitance. And of course, there also will be capacitance between the gate and the bulk through this, because gate and bulk, you can see there is some kind of flat formation is there. So there can be a situation where there will be a capacitance between this gate and the bulk. So we can see that different kinds of capacitance exist in this device, like that. So then how do we calculate it, and how do we estimate it, right? What are these values? That is an important point to discuss, like that. So I know I have many slides, but I think it seems it's already 1 o'clock now. So in the next class, we'll see how do we calculate all these parasitic capacitance, like how do we calculate this CGD, and how we calculate this CZS and drain to bulk, right? So this is a 3-dimensional view of this drain and source. 3-dimensional view of this drain and source. So then this capacitance C6 is actually divided into 2 kinds of CJ and CJSW. So we'll see in the next class what are all this, how do we divide these stuffs, and how do we estimate each of these C1, C2, C3, C4, C5, C6, like that. How do we estimate all this capacitance in the next class? Okay. Any questions?
No, sir.
Any doubt? Is it clear?
Sir, please share the slides with us, sir. Notes.
I have already sliced, like I have already shared in the website all the
Okay, sir.
so all the recording and the slides are already there. So you can just I hope you know the website, right? So you just go to my page,
Yes.
right it, and then all those things are already shared like that.